I believe I'm now live. So yeah, hello everyone and welcome back to LiveWork, where we are gonna be solving uh problems live. So yeah, today we are gonna be talking about um double integrals and also line integrals, which is one of the parts in line sorry in multivariable calculus. And um So yeah, in here we got 6 problems here from practice exam 3B of MIT OCW 1802 or multivariable calculus. So yeah, without further ado, let's just get started. Problem 1. Draw a picture of the region of integration of integral from 0 to 1, integral from x to x of dy dx. Okay, so first we want to draw a picture here. Okay, so yeah, the way that you actually draw the picture is that I will actually gonna be showing you guys the real picture, because like yeah, obviously if I just sketch it, it won't really help. So yeah, first things first is to draw the region of integration. So yeah, you first have the x and the y axis like so, and then after that this guy bounds from 0 to 1. Okay, and then you have here at the bottom side, that's y equals to x. So let's go ahead and just draw y equals to x. And then we also have y equals to 2x. Let's draw it like that. Okay? And so this thing here is going to be the region that we have here. This thing here is the region that we have. And that's actually like how you actually draw the picture. Like yeah, you just state that yeah. For the outer integral it is in terms of x. So yeah, it just goes from 0 to 1, and then for the y, it's just y equals to x to y equals to x. So yeah, that's actually how you would draw it. But yes, for me, um, because drawing in a laptop is pretty hard, so therefore, I have actually made it. I have made the I have made the graph in desmos. So let me just go ahead and just find that out. Yep, it's there. Oh, it couldn't be read due to an error, huh? Why does it have an error, huh? A bit curious. Let me just open up my Finder as well. So I can just double click on that. Yep. I mean, it's fine. Let's try this again. Place the due to an error, huh? Let's try this again. One last time, just in case. The file couldn't be read due to an error, huh? That's very weird. But I think I can actually open it in my preview. Yep. Yep. It can be read in my preview, so yeah. Let me just save it. Save it first and then just place it. Place. There's still an error somewhere, and I don't know why. Let me just move it to trash first. Okay. Let's try something else. Oh wait, actually, is my mic actually on? Oh yep, it's on. Good job. Okay. And so I'm just finding the or I'm just trying to find the original file. Uh, Somehow it is just corrupted. So yeah, don't mind the wait. Um, Somehow it's not really connected to it. Oh, okay. Some some crazy thing is happening. There we go. Let's open this up first. Um, um, okay. That's the f that's that that thing should be the file. But yeah, somehow it doesn't want me to do that. Okay, open that up. Yep. Okay. Let's hope that this time this will work. Yep, I knew it. Okay. So let me just shut some of these guys off. Okay. So let's try and put this guy in again. Place. If I can't, I will just actually just draw it. Yep. Wait, really? Is all of them having an error? Yep. All of them has an error. I didn't know about that. Oh. Which is pretty weird. Or does it actually not read JPEG files? Huh. Let me just do like a save as. Command Shift save. Okay. And then let me just try to put it in and see if this time it will work. Or maybe I'll take the screenshot of the thing, which is gonna be a bit much more work, but yeah, it works. I hope so anyways. I cannot actually find a copy of the thing. I don't know why. You know what? I'll just do one of the crazy things that I know of. Screenshotting. Because screenshotting somehow actually always works. So yeah, let me just move those guys to trash first. Then just place this. No. Okay, there we go. And there we go. Yep. So yes, you can see right here. That's the picture of the graph that we have here. So yeah. Oh, let me just actually just move this guy here, there. Huh. Okay. So yeah. In here you can see here that in here you got the line there. This is y equals x. That one there is x equals to 1. Then this entire thing going down there is y equals to 2x. And so this is the picture of this entire thing here. And now exchange the order of integration to express the integral in part A in terms of integration in the order of dx dy. Warning, your answer will have two pieces. Okay, so yeah, remember one thing, okay, is that you don't need to evaluate this integral. But yes, if you want to, you can just go ahead and just do it. But yeah, obviously I won't do it. So yeah, first things first is that let's just go ahead and just write the double integral dx dy. We are just gonna switch the order of integration. So we will do the integral. No, sorry. So that yes. So yeah, basically in here, we want the meaning to be like this. You want to sum up from somewhere to somewhere in the y terms, and then you want to sum up the entire thing from something to something of the x terms. Okay. And so like yeah, that's basically how I explain it. But yeah. Oh, but yes, it is something like this. Okay. You will take a certain value of y, and then after, well yeah, actually, like yeah, you are gonna sum up from here to here. that's that's the y direction, so that's from 0 to 2. No, don't. So yeah, don't. So first thing is that you don't do it from 0 to 2 because obviously it doesn't work. So yeah, this is why that I have here another one here. So basically like this. You want to sum up the entire thing from here to here, okay? And then this guy here is actually a function that actually scans the x direction, something like that. But yes, when you actually just look at this, you can see that there's like two functions here for the maximum term, which is this function going like that way, and then the function going like that way. And that thing actually requires you to actually to split it up into two terms. So yeah, and here you could actually just split it up into two terms, so that you can actually just sum up the one that is vertical, and then the one that's going diagonal. Okay, and so after that, when you have figured out the y bounds, you want to figure out the x bounds. So yeah, the x bounds here will start from this point here, which is y equals to 2x, or you could write it as x equals to y over 2. That is the lower bound for both of them. So it's both y over 2 there, and then for the maximum one, it's y equals to x. That means x is equals to y, like so. And then for the one that goes from 1 to 2, you can see that this guy here is x equals to 1. Therefore, this guy will go until 1. And this is actually the answer. It is a pretty simple problem for you to actually solve, and yeah, that's that. So yeah, you could just actually go ahead and just evaluate it yourself. What you'll get is actually something. Let's see. I believe it's 1. Like yeah, I believe it's no, I don't think it's, yeah, it's half. Like yeah, the answer is half. But yeah, if you don't know how I get it, you could just go ahead and just do the integration just by first integrating the one on the inside, and then after that you just want to integrate the outsides. And yeah, treat the y as a constant first, and then after that just do the entire integration in terms of y. That's how easy multivariable calculus is. I know I am a bit exaggerating things, but yeah, that's that. Okay. Part 2. Problem 2. find the mass of the upper half of an annulus 1 less than x squared plus y squared less than 9, where y is bigger than equal to 0, with density delta equals to y over x squared plus y squared. Okay, so yeah, I also have the picture, but yeah, I obviously graphed something different. Delete the copy first. So yeah, in here, let me just take the screenshot of this. Wait, actually, can I just copy paste this? Copy paste that. Oh yeah, I can, but it is a very big shape. So let me just rescale it down. Let's just rescale it. There we go. So yeah, basically this thing here is the shape. I graphed this on GeoGebra. So yeah, you could see that, yeah, in here that we have this tiny circle here, which is the boundary from the x squared plus y squared is 1. Or it's basically a circle with the radius 1, and then this outer circle here represents when r equals to 3. So let me just retrace that guy up. There you go. This guy here is the radius equals to 1, and this guy here is a circle with the radius of 3. And yeah, by the way, in here, it is being said that, yeah, you want to take the upper half of the annulus. So yeah, you can just actually ignore this guy, because like, yeah, this one here is the y-axis, the green one. So yeah, you could actually just you could just ignore this part here, and we want to figure out the mass of this right half that we have. We want to figure out the mass. Well, yeah, by the way, this thing here is actually only a representation, because like, yeah, the the reality is that it is a disk, but yeah, the density depends on this function y over x squared plus y squared. Okay, but yes, when we have this disk, for me, I would actually just represent it like, yeah, the thickness is actually a bit changing, but yeah, obviously it's not. But yeah, you could actually just write it something like this, okay? And so yeah, I will just actually just leave this guy in here. So yeah, the way for you to actually to solve what the mass is that it is it is a pretty straightforward thing. Well, yeah, it is not really that straightforward, but yeah, it's the double integral of the region, and then you take the density, multiply this by dA, the change of area. And yeah, in here, the most easiest thing for you to do is actually to convert the entire thing into polar coordinates. Going polar in here would be so easy. And yeah, by the way, this guy here is exactly when theta is 0. Theta is 0. This guy here would be when theta is pi. Okay? And so, when you just do the integration here, we first start from 0 to pi, because we want to do d theta at the very end. And then for the radius, it would be from radius 1 to radius 3. It is never changing, so yeah, we were lucky to get that. And now for the density, the density here is, okay, so in polar coordinates, the way that you say x is r cosine theta, and the way for you to say y is y sine theta. And remember that r equals to the square root of x squared plus y squared. And this is exactly why the bottom side here is actually r squared, because r squared is basically x squared plus y squared. And so what's y at the top? It is something that we have already computed. It's r times the cosine theta. No, r sine theta, because this thing here is the y direction. But we are not finished when we actually apply this. You need to multiply this again by r. And in fact in here r actually cancels each other out, which makes this guy here only the integral from pi to 0 of the integral from 3 to 1 sine theta dr d theta. And this is a very easy thing for you to solve. You just go ahead and just integrate sine theta in terms of r. So basically you just take theta as a constant, which means sine theta is a constant. That means that you just want to integrate a constant, which is basically a simply r sine theta. R sine theta, and then you evaluate that from 3 to 1 of d theta. Computing this, you would get actually the integral from pi to 0 of this guy here. We just go ahead and just plug the r in. So it's 3 sine theta minus sine theta. That would be 2 sine theta. 2 sine theta. And then after that, you want to integrate the 2 sine theta from pi to 0, which is a very easy thing. It's negative 2 cosine theta from pi to 0. And yeah, cosine of pi is negative 1, so that's 2. And then minus that by negative 2 times 1. So that's a total of 4. And this guy here is actually the mass of the object. So yeah, it's a pretty quick thing to do. Okay, good. And so now, express the x coordinate of the center of mass x bar as an iterated integral. Write explicitly the integrand and limits of integration. Without evaluating the integral, explain why x bar equals to 0. Okay, this is something that you need to also know. Is that center of mass is 1 over the mass, which in this case is 4, and do the double integral of the region of the one that you want to actually to take the thing on, which is x, and then you multiply that by tilde of dA delta actually of dA. There we go. And this thing is basically what the formula is. You could actually, well, wait, obviously you want to actually to write it as an iterated integral, obviously. But yeah, in here I would just write this down as a quarter of the integral from 0 to pi. The same stuff from 1 to 3. And then this guy here is going to be xy. But then I want this to be in terms of r. So I would get an r squared sine theta cosine theta divide the entire thing by literally r squared, multiply this by r. Okay? dr d theta. And so when you actually just simplify the entire problem up, you'll get a quarter from pi to 0 of 3 to 1 of r sine theta cosine theta. You could actually simplify this much more just by turning the sine theta cosine theta into a sine 2 theta over 2, and then you just actually just calculate the entire thing, and then you just figure out that that would equal to 0. But but then in here it but then in here it just asks you, without evaluating the integral, explain why x bar equals to 0. And here's the reason. This thing here is actually symmetrical in the y-axis. Like, yeah. How do you know it's symmetrical? You can just go ahead and just plug in x equals to, when you just plug in x and negative x, same thing will come out to you when you put it inside this density function. So that means that, yeah, it is it is it is it is a it is a symmetrical object within the y-axis. And then when you actually just crack the entire code up, um, when you get something which is symmetrical within the y-axis, you know for certain that, yeah, x bar would obviously be 0. So yeah, why is it x bar equals to 0? Because that it is symmetrical. It is symmetrical. But another way that you could actually just look at this is that, yeah, just like what I said, is that this sine theta, cosine theta could be converted to sine 2 theta over 2. And then when you should just do the integral, the sine theta, no, sorry, yeah, the sine 2 theta over 2 would actually still be there. And obviously sine 2 theta, when you actually just integrate it, you would get like a cosine 2 theta over 4. But we will only care about the cosine 2 theta. When you plug in cosine 2 theta pi subtracted by cosine of pi, no, cosine of 0, you are just literally getting a 0. And that's the reason why that, yeah, the answer is 0. But yeah, also the reasoning could also work when you just say that it is symmetrical. So that's why x bar here is 0. Okay, good. Next up here. Okay. Show that f equals to 3x squared minus 6y squared I hat plus negative 12xy plus 4yj is conservative. B, find a potential function for f. C, let C be the curve x equals 1 plus y cubed 1 minus y cubed from 0 to y to 1. Calculate that entire thing. Yep, it sounded like that. I was pretty lazy to read the entire thing. So yeah. Okay, so first things first, that show that f 3x squared minus 6y squared with this guy here is conservative. The way that you actually solve this is actually a pretty neat thing. Is that you could actually use Green's theorem straight away, but what you can actually do is to figure out the curl. So assume here this guy here to be m, assume this guy to be n. So the way that you actually find what curl is, the curl of f, it would equal to n and n of x subtract this by m of y. Like, yeah, I mean, like, yeah, you just need to derive it. And this is like basically the stuff that you have actually gained when you have actually learned about partial derivatives. And yeah, this is basically how you actually write partial derivatives. And so when you actually just do this start thing, n of x, that's minus 12y plus 4. Nope. When you just derive it by x, yeah, the 4y will actually turn to a 0. And then you subtract the entire thing by m, but then you just need to do it in the y direction. In terms of y, which is 12y. And this would equal to 0, which actually proves that this guy here is actually conservative. And so conservative is basically it is path independent. So like, yeah, any path is fine as long as you follow this start thing. And yeah, so now we want to find the potential function for f. So what's the potential function? Well, there are multiple ways that you I should do this. For me, like yeah, obviously, okay. So like yeah, m here. Let's just start with m. 3x squared minus 6y squared. Okay, this guy here is actually, you could call this as a function. This like yeah this like this potential function, but then you just subscript it with x. And so when you try to figure out what f is, you just need to take the antiderivative, or you could say an integral. But yeah, for me, like, I would just straightway just write this guy down: x to the power 3 minus 6xy squared plus a constant. But this constant here is actually a function of y as well. And so when you're actually just doing this f of y, what you'll get is actually a minus 12xy plus c derivative of y. Well, yeah, it's not real derivative, but yeah, you just take this guy there, so it's x point y. Like, yeah, I normally forgot about it, but yeah, you just need to take it, the cy there, and then you just need to figure out what cy is, which is a very easy problem because like yeah, you know. So yeah, in here, when you actually just see what n here is, it's minus 12xy plus 4y. That means that you know that cy is 4y. And so you could actually just conclude that c is 2y squared when you just integrate that, plus uh plus plus a constant. So like yeah, normally like yeah, you just call that a g probably. Like yeah, or like yeah, a g would make sense. And so when you actually just put in what the potential function is, it's gonna be 3x squared. No, sorry, my bad. This would equal to x cubed minus 6xy squared plus this 2y squared plus constant. And yeah, that's basically the entire function. That's the entire potential function. And so I want to show you this picture here. Copy this, paste it, but not that big. I still need to try to figure this out. So like yeah, shrink it down first. Put it there. There you go. And can I place it now? Obviously it would be a no, but yeah. I'm still like testing things out. Place that. Nope, it couldn't be done. So yeah, you just need to copy paste the entire thing again and again. Let's see. Where is it? Oh yeah, it is at my Finder. Copy that, paste that. let's just try to shrink it down. Okay, so what I have here is actually the function that you have. This guy here, the one the the one on the left is the vector field. The one on the right is it is a something something like like the left side the left side is a the left side is a vector field. The right one is the function that we want to calculate here, which is actually the curve C. And yeah, basically you can see that basically like in here like this plot actually tells you about the gradient of it. Like the vector field actually like shows you like for the potential function that you have what um which way is downwards. I guess that's how you say it. No, but yeah. Oh wait, actually no. It's like it is like talking about where is the peak, I would say. No, I don't think so. But yeah. By the way, I am not really an expert in actually doing this vector fields because obviously I just took the course, but yeah, I'm here just trying to explain it to you all. So like it is like the gradient vector that you have. Or like the gradient vector is actually a vector that is perpendicular. No, a gradient vector actually shows you about how steep it is at a certain location in the x and in the y direction. And when you just plot them all into a plot, it tells you which direction would actually goes into the higher point, I believe. I believe that's how you actually read it. Because obviously if you have like for example a function like f of x, you just take the derivative and then you'll later find where the positive and negative, and that will actually show you how high or where it goes. Does it goes up or does it goes down? Um, well, actually, yeah, technically that's true. But yeah, oh yeah, it is true that where it is pointing is actually the higher point of the three-dimensional curve, which is something that I don't actually draw in here because it is not really that important because what we care about is the vector field. But yeah, anyways, continuing on is that um the line that we have in here, the 1 plus y cubed 1 minus y cubed is the one on the right, the red one, because we are just evaluating this when y is between 0 and 1, which is pretty much looks like a straight line, but that is not something that we actually need. The only thing that we need is the final point and the initial point, because this thing here is a conservative vector field. So in here, when you have 0 to 1, you just plug the entire number in. You would get it starts from 0, so you just plug in x equals to 1. Yep. So you get a 1.0 from the initial, and then it goes to something 0.1, which I believe to be 1.1. Yep. And so you just need to evaluate what is what is the vector field? No, like yeah, because like yeah, because this guy here is actually path independent. I could just like say like yeah, this guy just goes straight way up. It's just the same thing because like it is path independent. So so if I go and just say that it just goes straight up straight away, that means that it's x equals to 1, while the change of x would mean that it would equal to 0. And so I don't need to care about uh so yeah, when you just put into the when you just put it inside a linear integral form, like yeah, you just need to transform the I into a dx and then the j into a dy, and then after that you just need to find the relation between x and y, maybe introduce a new variable like t or theta, but yeah in this case it's unnecessary. And so like yeah, you will have a minus 12xy plus 4y, but then obviously x is 1, that means it's minus 12y plus 4y, which is actually minus 8y. So let me just write that down. Minus 8y dy. Evaluated from y equals to 0 to 1. And this would actually equal to, when you just solve the entire problem, that will be a yep. The answer would be a negative 4. And why is it a negative 4? Well, yeah, you could actually just see that when you actually just go up, something like that, the vectors actually go downward. Like, yeah, it's, like, yeah, it is just want to ruin your work. That's why it's a negative. And so, like, yeah, you just figured that entire thing out. Good job. Okay? And so now, let's actually go into problem 4. Okay, express the work done by the force field F equals to 5x plus 3y on a moving counterclockwise once around the unit circle centered at the origin in the form. Uh, uh, okay. Okay, so yeah. Um. Oh wow. Okay. Hmm. So first thing first is that you obviously check if this guy is a conservative force or not, which I know, which I know is that it is not gonna be something that I like. Yeah, but yeah, for problem A, you want to express this entire thing as an integral, which is totally fine by me. So yeah, when you just do work done, you just change into a dx and then a dy, but then you want it to have only you only want this to have one single variable. That means that I'm gonna be changing x into cosine theta, y into sine theta. But then you will actually see why I actually got this problem. Like yeah, when you just integrate this um from point 0 to 2 pi, which is basically the theta, and then you just plug in the entire numbers in. Like yeah, x, when you just plug in x, then it would be 5 cosine theta plus 3 sine theta, and then you just multiply the entire thing by I hat, which in this case I hat is actually, when you just compute what the integral of cosine to theta is, it's going to be a minus minus cosine theta. What? No, yeah, it's a it's a minus sine theta d theta, and then you add this by 1 plus cosine of sine theta. Now this is something a bit stressful because like just by sudden you got a cos, and then just by sudden you got a sine inside this cosine, which which is why that the problem maker doesn't want us to solve this problem straight away. cosine theta d theta. Okay, because like yeah, sine theta integrated at cosine theta d theta. Okay, and so now instead of actually just doing this, instead evaluate the line integral using Green's theorem. Green's theorem actually solves the entire problem because like yeah, it turns this very hard problem into something much more manageable. Like yeah, in here Green's theorem would basically state that yeah, this guy here would be the integral from, this would be the double integral of a region. And then remember you want to take n and then just evaluate at x, which would basically be 0. Subtract this by m, take the derivative in terms of y, it would be a 3 dA. And this would actually solve the entire problem. And I know what the answer is. It's actually negative 3 pi. Why can't I straight away just determine the entire thing to be pi? Just by sudden, out of nowhere. Like yeah, because I know what the meaning of double integral of r dA. Double integral of r dA is basically the area. And what's the area? It is a unit circle, which is pi r squared, or r is 1, that means it's pi. Therefore, you get a minus 3 pi. And actually, I have the picture of the vector field. Let's just open this up. Like yeah, I am just doing this for show and tell, because like yeah, obviously these things are cool. Like yeah, you could see like yeah, it is a pretty ordered vector field, I would say. Like yeah, but yeah, what you do is that you just actually like yeah, in here you are just evaluating this entire thing here. Okay, it moves counterclockwise as always. And yeah, when you actually just try to calculate the entire thing, you would see that most of them actually goes against most of them goes against this circle. But yeah, some of them still goes with the circle, which is why that yeah, the work done is actually mostly a negative. So yeah, that's what. So yeah, like yeah, that's actually the explanation why it is a negative, because like yeah, the work done is actually like yeah, it should be a negative, because like yeah, when you just sum up the entire vectors contributing to this vector, to this trajectory, most of them will end up actually going against it. So that's why. Problem 5. We got 2 more problems. Good. Okay. Consider the rectangular R with vertices 0, 0, 1, 0, 1, 4, and 0, 4. The boundaries of R is the curve C, consisting of C1, the segment from 0 to 0 to 1.0, the segment from 1.0. Yeah. Okay? Yeah. Okay. Consider the vector field that. Find the flux out of R through C. Show your reasoning. Okay. So when we consider about flux, like yeah, it's just flux. We don't, like yeah, I don't really care much about flux, because like yeah, flux is actually a very easy thing to actually figure out. Well yeah, in here it's just say like R through C. That means that you want to figure out the entire thing out of R through C. So yeah, You are just trying to find out what the flux is on R, on this region. Well, there is two different methods. One of them is that you could just compute the line integral, which is a bit too much, I would say, because like you would actually just need to separate the entire thing, or you could actually just take the Green's theorem for the flux, which is a pretty similar one, but yeah, instead it's actually px plus qy. I think it is. I think it is. Uh, it's like, yeah, you first actually just change the thing to dy dx, and then just, yeah, yeah, I'm correct. It is px py. And so when you actually just evaluate what px is, px would be a y plus cosine x cosine y. And then you add it up with with this guy here, evaluate qy, that would be actually a minus cosine x cosine y of dA. And then you can actually just cross these two up, and then you would get the region y dA. And so you just need to set up the bounds, which is actually a pretty easy thing to do. Let's actually just do the x first, and then after that the y. So the x goes from 0 to 1, and then for the y it goes from 0 to 4. Oh wait, I just did that reversely. Oh well, it's fine. dy dx. And so when you just compute y squared over 2 for 0, that would be an 8. Well, actually the answer here would be 8. Because, like, yeah, some mental calculations allow me to actually do the entire thing straight away. So, like, yeah, it seems that, like, wow, that's so like, yeah, you just basically just compute the inner integral and then just compute the external integral. And I also have the vector field for this. Let's just take the screenshot as well. Copy that. Paste that. Shrink this guy down. There we go. Okay. So now, yeah, this picture here actually shows you the vector field. You can see that most of these are like horizontal, but yeah, some of them are not. But yeah, it doesn't really actually matter about what this picture actually does. But like, yeah, when you actually just read in here, it goes from 0 0 to 1 0, and then 1 0 to 1 4, and then 1 4 to 0 4, and then from 0 4 to 0 0. So yeah, basically, so like, yeah, the path of it actually traversing is actually a pretty simple path. You go along this way, and then you go up, you go back, and then you go down. This movement is counterclockwise. And yeah, by the way, this thing here, actually the x-axis only goes to 1. So yeah, that's that. And so with this, actually, let's call this C1, C2, C3, and C4. And yeah, by the way, flux is actually just by taking, like, yeah, you just take the part that is contributing to the one that is heading towards the right, which is mostly from the C2. You could actually see from the graph, but obviously you cannot actually So you will see it when you just solve the problem. But let's actually just do it and just tell it why. Is the total flux of R through C1, C2, C3, R through C. Show your reason. So like yeah, you just first solve the entire problem. This one here is y equals to 0. This one here is x equals to 1. This one is y equals to 4. This one is x equals to 0. Okay? So like yeah, first things first. C1. When you just plug in C1, okay, just when we do the mental calculation, y is 0. Okay. When y is 0, that means that most of them will actually turn to 0. Sin y there turns into 0. Wait, don't forget about one thing, okay? We are talking about flux. When doing flux, you just actually do one or like yeah. You just do like one weird thing, which is just basically you just basically switch the position and then just add a negative at the end. I don't know. Like yeah, switch like yeah, you first switch the position like that, and then just add the negative sign at the end. Well, yeah, not really that correct, but yeah. You like yeah, you just actually just flip the sign on the j hat direction. Totally weird, but yeah, it is correct how I actually describe it. Sin x cosine y, and this is dy. This one here would be dx. So yeah, dx here. Okay, so like yeah, in here dy is 0. Okay. So that means like yeah, we can just ignore the backside, and then the y is 0. That means sin y is 0. That means the entire thing is 0. So this guy here would be 0. C1 is 0 basically. So like basically when you actually just plug the entire numbers in, you would get a 0 flux. For C2, when you just plug the numbers in, doing the mental calculation, dx would equal to 0. Therefore that y plus sin x, no, y plus sin, oh wait actually, like yeah, it's correct. So when you just plug in that, like yeah, dx is 0, but then x is 1. Therefore y plus sin 1 cosine y dy must be something, which is something that you need to evaluate. Okay. Wait, actually, why actually? Like literally, why? Like, yeah, it doesn't really make any sense. The more I think about it, when y is 0, dy is 0, yeah. So like yeah, I know like the bottom side there is 0. C2 is something. Like yeah, when you just glide it in, it should be correct. That guy should be correct. That guy should, like yeah, this guy should be less than the thing. But I don't know how. Well, actually, like, oh wait, no, actually, I cannot actually discover the entire thing. You know what? Let's go with part B. Okay. First one, C1 would be 0. We know about this. For C1 is 0 because like when you just plug in entire numbers you would get that. But for C2 it's it's a bit different. You just basically take the integral of the start thing. Um, dx is 0, okay. Um, what you have is actually a y plus sine 1 cosine y dy. Computing this from 0 to 1, which is totally weird, but yeah. When you just compute this, it's actually like 1 plus sine 1 cosine 1, subtract the entire thing by that guy 0, and then subtract this by sine 1. No, that's not how you actually compute this entire thing. Obviously. Like, yeah. Y, that's y squared over 2, that's half. And then cosine y, that would be sine y. Sine y, plug in 1, so you would actually get like a plus sine squared 1. Subtract the entire thing by, when you just plug in 0, okay, that's 0, subtract that by sine 1. No, 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 no. When you get 0, you're lucky, nothing happens. you're lucky, nothing happens, yeah. Okay. Actually, this thing should go from 4. So sine 1, sine 4. This guy should be 8 plus that entire thing. So yeah, that's basically the calculation. Like, yeah, it's more than 8. Okay, we got that. C3, computing the entire thing. Same stuff. dy is 0. Ignore the backside, but what you have is cosine x sine 4. Yep, you got cosine x sine 4, which is something that you need to integrate yourself of dx there from 1 to 0. And I'm so sorry if I actually jump because like yeah, it's something that I normally love to do, but yeah, obviously it's unhealthy. So yeah, what you get is actually sine 4, subtract that by sine 4 cosine 1. No, 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 no. When you when you just do the integral, like yeah, it just turned to a sine x. Sine x 0, that's something, but then yeah, this guy would be sine 1 sine 1 sine 4. And somehow it's a negative, but intuitionally intuitionally it shouldn't be. How could I actually explain this? But yeah, intuitionally it shouldn't be. Well, actually, y is 0, y is 4. So like yeah, you will actually get that. Yeah, that's correct. And then when you plug the entire numbers in, it's actually sine x. That's actually emerging out. My logic is starting to diminish a bit. But yeah, somehow the flux actually is reduced. Oh yeah, flux is actually no, 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 no. Flux shouldn't be reduced. But yeah, C3, that's like something. is the total flux from C1, C2, and C3. But yeah, C4 we don't really care because C4 doesn't really have any flux. So yeah, from C1, from 0, 0 to 1, 0, you have actually computed the entire thing. When that's when y is 0, therefore plugging the entire numbers in, most of them will cancel, and then after that you know what dy would equal to 0 anyways. So yeah, somehow it is cancelled by the one going to the top there. Like, I don't really understand where does that not force, but yeah, where does that thing actually come from? But yeah, somehow that's that. So this guy here is less than the flux that you have, 8, because of when you actually just draw the entire graphs in. Okay, I just do it by calculation. I know, but yeah, I know my explanation is so bad, but yeah, I'm trying my best to improve. But yeah, let's actually go to problem 6. Find the volume of the region enclosed by the plane z equals to 4 and the surface z equals to 2x minus y plus x plus y minus 1. Suggestion: change of variables. Well, yeah, obviously, I have actually the picture, but yeah, obviously, it's not gonna really help you a lot. And so, how would you actually compute the volume of this region? Um, like, yeah, you could actually just see this straight away that yeah, um, you take triple integrals. Didn't see that one coming, huh? Like yeah, like yeah, actually like yeah, it's not really that hard per se. Like yeah, the volume is just simply you just sum up those bars. So like yeah, you just basically take the double integral of this entire thing. You just take the double integral of the region that is actually covered by this entire thing, which is 2x minus y squared plus x plus y minus 1 squared dA. And obviously you don't really want to actually solve this crazy thing, so yeah, you'll just do change of variables where 2x minus y is u and x plus y minus 1 would be v. Okay? And so when you just do Jacobian, which basically you just take ux, uy, vx, vy, you'll get actually as 2 minus 1, vx, 1, 1. So when you do the matrix there, that's a 3 total. And so you would actually get like, yeah, du dv over 3 is dx dy. dx dy. That's literally how you actually use Jacobian for. And so you could actually just compute the double integral of the region. U squared plus v squared. And then this dA here. dA in here would actually represent something else, which is actually the du dv over 3. Okay? But then now, here comes the most trickiest part, is that you need to graph the entire thing. Like yeah, first thing first that yeah, you want 4 equals I literally just figured it out straight away. I did actually do something a bit wrong, but who cares at this point? So like yeah, you want to figure out what is like yeah. When you like yeah, you just figured that u squared plus v squared is something equals to z. And so therefore, you know actually what u squared plus v squared is actually it is actually a parabola going upwards. Like yeah, its mount is going upwards. So yeah, that's something that I discovered. Um, this thing should actually be 4 minus. That would make the most correct sense because like yeah, now the parabola is actually enclosed at a certain stuff, you know, those kind of stuff. But then you just try to figure out that yeah, u squared plus v squared equals to 4 is the limit. Therefore, you know what u and v is. It's a circle with radius 2. Radius is 2. And therefore, you could actually just straight away just turn this entire thing into polar, which is 2 pi towards 0 of this other guy from 0 to 2 of this entire thing of 4 minus r squared, multiply it by r, divide the entire thing by 3 of dr d theta. And now this thing is where most of the calculation actually takes part. So like yeah, you'll actually get 2r squared over 3, subtract this thing by r to the power 4 over 12, evaluate it from 2 to 0, integrate it from 2 pi toward from 0 to 2 pi of d theta. Okay. And so when you just plug the number, that's 8 over 3. Subtract that by this starting. 8 over 3. That's 8 over 3, and then for that one, it's 4 over 3. So actually the answer is 8 over 3 pi. After all of the integration, and that's the answer. And I know I didn't actually explain lots of things here, but yeah, I hope that you could actually understand how I actually think, not actually explaining about the problems that I'm actually trying to teach. But yeah, I hope that you could actually see how I actually think, because this is the main concept of LiveWork. So yeah, I hope that you guys can find this thing helpful, and yeah, we'll actually meet you guys later at the next